Yeah. See. Okay. And Gauss was really interested in the sort of the to describe the sort of the shape of this surface. But shape of surface is difficult to say what is the shape of surface. So he really wanted to the how much this surface curved. It curves in quite different directions. Okay? And he wanted to introduce the sort of the curvature. So curvature is described as how that your surface are curved. It's in a sense of tautology. Okay. So what Gauss did is as follows. So it's rather difficult. No, not difficult. So you start. You have a surface here, and here that's the tangent plane direction, and this is normal one, and then cut this surface. So cut. Cut the surface as plane. Containing this C. So, of course, containing C and P, it's better to say. Okay? So there are many surfaces, planes, not T, sorry. Plane. There are infinite many. Okay? Planes. But if you cut this plane, some curve appears here. Okay? And for the curve, you can define the sort of the curvature. Always. Sometimes in elementary calculus we do, but I think today probably we don't discuss about this curvature. What is the curvature? So just come back to the plane, and plane in the curve, and you point P, and near point P prime. And you take a tangent line here, and you take a tangent line here, and P. So there are some small difference of the angles. Then the curvature for the curve is curvature. K, its curvature, is defined by what is it? This length, and divided, maybe this is the small delta theta, and take a limit, P prime to P. That's correct. I hope it's correct. So PP is, maybe I just said this is, maybe I said just delta S small. So this is, maybe better say more precisely, this small length delta S, not direct. It's of course it's the same. Taking as P prime or delta S is also same. So maybe it's better to say P prime P prime. And Gauss really wanted to calculate this for each of these planes, and want to find when it becomes maximum. So how can you calculate this? And there are two possibilities. The one possibility is, it's really the invention of Gauss, is starting from this your surface, and P, and then he maps to this to S2. This is a two-dimensional sphere in 3 space in Y. You can find always normal unit vector CP, and so from the if CP, you may consider this as a vector from the origin of this. Then it gives you some point in S2. So if you change this P, then this point moves around. Yeah? And that's called, how to write it? Zeta? It's called Gauss map today. Because Gauss introduced this. And then he found that, he defined that if you choose some small area here, the epsilon, some small, for example, small disk-like space here, and then compare its image by zeta. So it's a normal vector is changing. Yeah? So that gives you some point. For example, that if that normal vector is just always same, that gives you that this map is just 1 point. Yeah? So that means that normal vector is same. It means that your surface is flat, locally at least, because the tangent plane is always same. It means that its surface is almost same to the tangent space. Okay. So the one possibility is just compare the area, the epsilon, and the area of your, and this gives you how that the surface is curved. That gives. And of course, each point you take a limit. And you give some numbers here. But since this is just area, this doesn't give the precise answer, but this gives you sort of the absolute value of the curvature gives. And of course, you can introduce a kind of the signature of the, because you can introduce a notion of the orientation. So the orientation means which is the upper side and which is the lower side. And then whether this mapping preserve this orientation or not. And then in this way you can introduce the sign here, then you can drop this absolute value. But somehow Gauss could define that the curvature or absolute value of curvature using Gauss map. This is Gauss's one contribution to the differential geometry, but he did more. So just coming back to using this very simple notion of the curvature, he really wanted to calculate more effectively this K. So it really depends on what kind of the plane you cut this. And then what Gauss found is another interesting thing. So for that purpose, we have to introduce another form. Oh, by the way, I forgot that this is, I said metric, but in the terminology of the Gauss, this is metric, but Gauss say that this is a DUDV. Sorry, yeah, 2 times, yes. And this is the first fundamental form. He named it. And then to describe the K, you need the second fundamental form. So Gauss described LdU, Lm 2 times du dv plus m dv. Yeah, what is it? This is, yeah, it's just going back to the, it's quite difficult to write down and draw the picture. I'm very bad for drawing the pictures. So you have a tangent line at point P. This is the x u v. And then if you move this point slightly here, and tangent line is just you take the first order relation. And so if you choose also second order, so x plus x u du, dx plus 1/2 of, and here, so what I wrote it, x u du square plus 2 times x u v du dv plus x v of dv square. Okay. Then it does not touch to this tangent line. So now choose this point and try to find out the length of this distance between this point and the distance of this point and this tangent line plane. To P. And actually, we already defined that the normal vector C. So it is very easy to show that this is a kind of the difference here. And we just want to take the part of this normal direction, then you get the length of this h. And that you can actually write down, so nothing but this is a C times 1/2 of the xuu. This is a vector product, inner product, d square, plus C times 2 times C of x duv, duv dv, plus C of xvv, dv square. Okay. Please note that C can be written using the xu and xv, and this comes in the second derivative. And this is nothing but. So his second fundamental form is, this is the h actually, and 2h is sort of the second fundamental form of Gauss.
What is C?
The just what's it? The ratio of the second fundamental form and first fundamental form. Okay. So the reason is actually, in here you need to calculate delta theta, p prime, and actually you can write down using that p prime p in this case. So you just choose this part, then you can just find that this is nothing but square root to 2h. You can write in this way. So that the pp prime is just the length, small length, so that disappears, and 2h is nothing but that one. Okay, so that's a good view. And actually, the reason is something like this here. If you look at this more carefully, and then this you can replace it the sine delta theta, because delta theta and sine delta theta is almost the same difference.